Today I will be talking about the aldolase mechanism. First of all, what is an aldolase? It is an enzyme that catalyzes the following reversible reaction. Fructose 1,6-bisphosphate, or F16BP for short, is cleaved into two products, dihydroxyacetone phosphate, DHAP, and glyceraldehyde 3-phosphate, G3P. Let's discuss the overall context of why this reaction is important. It's used in both glycolysis and gluconeogenesis. For glycolysis, we start out with glucose, and we want to get energy from it in the form of ATP by converting it into pyruvate. The glucose is converted into F16BP through a series of reactions. Then the aldolase reaction produces these two products, which will both ultimately be converted into pyruvate, producing ATP in the process. The ATP is used to supply energy for metabolic reactions in the cell. Recall that this reaction is reversible, so we can also go in the opposite direction through gluconeogenesis. If we have a lot of ATP and we want to make glucose, we can begin with pyruvate, get DHAP and G3P, and then stick them together into F16BP using the aldolase reaction. The F16BP can then be converted into glucose. In the liver, the resulting glucose could be released into the bloodstream to supply fuel to other tissues, or it could be stored in the form of glycogen, so we have access to sugar even if we haven't eaten for some time. Now let's get into the main discussion for today, the mechanism of how this enzyme works. Recall that enzymes are catalysts. They lower the activation energy of a reaction by stabilizing the intermediates. In this case, cutting up fructose 1,6-bisphosphate into two products by carbon-carbon bond cleavage results in an unstable intermediate. So the enzyme must act to stabilize this intermediate in particular. There are two classes of aldolases, meaning that we have two different methods to stabilize the intermediate. The class 1 aldolase uses a lysine amino acid to form a Schiff base or imine intermediate. It's found in animals and plants. Class 2 uses a zinc ion to stabilize the negative charges on oxygen. It is found in fungi. We'll first talk about the class 1 mechanism, and then we'll talk about the class 2 mechanism. For class 1 aldolase, the first step is to convert F16BP from its ring form into its linear form. This is the exact same molecule here, just in two different forms. The ring form is much more common in the cell, but the enzyme active site contains catalytic side chains that allow it to easily convert into the linear form. A basic side chain deprotonates the hydroxyl group, causing these electrons to come down and to form the ketone. This leaving group gains an H+ and is in fact this OH group in the linear form. The next step is to form a Schiff base. The nitrogen on this lysine side chain of the enzyme does a nucleophilic attack on the ketone, causing this intermediate to form. The water then comes off as a leaving group, resulting in the Schiff base. Now we will cleave the carbon-carbon bond and release G3P as one of our products. A basic side chain comes in here and deprotonates the hydroxyl group, forming an aldehyde and then cleaving the single bond right here. The electrons go to form a double bond intermediate with an attached amino group that came from that Schiff base. This product here is G3P, one of the products of the overall reaction. So now we just need to convert this other intermediate into our other product, DHAP. We need to hydrolyze the Schiff base in order to turn this molecule into DHAP. First, the electrons on the nitrogen come down and reform the Schiff base. Then, water comes in and does a nucleophilic attack on the Schiff base. This lysine then comes off as a leaving group and can be used to catalyze the reaction with a new molecule of F16BP. We can also see that we've now formed DHAP as our product. Next, let's look at the mechanism of the class 2 aldolase. Step 1 is exactly the same as for class 1. The F16BP is converted from its ring form into its linear form. Now the carbon-carbon bond cleavage step occurs. You can see as the single bond is being cleaved here, these electrons come up onto the oxygen, causing it to have a negative charge. But there is a zinc ion here which has a positive charge and is able to stabilize the charge on that oxygen. Just as before, we've already formed G3P, and we'll need to convert this other intermediate into DHAP. Here you can see the electrons come back down from the oxygen, forming DHAP, and the reaction is done. To summarize, let's compare the two classes of aldolase. They both catalyze the reversible reaction of F16BP into DHAP and G3P. Both classes start with converting F16BP from its ring form into its linear form. The class 1 aldolase then proceeds to form a Schiff base. The carbon-carbon bond is cleaved, and G3P is released. Then the Schiff base is hydrolyzed to form DHAP. The class 2 aldolase does not use a Schiff base at all, and instead uses a zinc ion in the carbon-carbon cleavage step. Just like for class 1, G3P is produced right away, and the other intermediate is converted into DHAP. The Schiff base and the zinc ion act to stabilize the intermediate, allowing the carbon-carbon bond cleavage step to occur at a reasonable rate. That's all for this video. Thank you for watching.